Okay, for the recording, before we get into the exam review that has previously been published to Blackboard, this guy, we're taking a special question from the homework somewhere, and the question is this: the height of the cars or the people on some kind of a ride, like at a carnival, is given by this rather complicated function, where the height is in meters and the time is in minutes. The time that the ride begins is time equals 0, and the question is, when will the ride function be 27 meters above the ground? Find the time that will make that true. So we take this expression on the right-hand side, set it equal to 27, and what we've done so far is simply add this ugly thing to both sides of the equation over here to make it positive. And on the left-hand side, we'd get 17.6 minus 27, which is minus 9.4. And I've switched the left and right around just for convenience. And then my next step of algebra would be to divide both sides by 15.5. And this is something I can get on my calculator, of course. So I'll be taking the inverse cosine. And that's a calculator thing there. And then I'll multiply each side by 5 and divide each side by pi to get my answer. I said divide by pi, divide by 2 pi. So this does the algebra. And the arithmetic is kind of intense, but it's intended to be a calculator problem. Okay, so what I'm going to do is, first of all, presumably this is in radian mode. So let me check my calculator, radian mode. And then I'm going to basically just type this thing in. So I think it might be actually easier to do this in 2 steps. So I'm going to take the inverse cosine. I'm just working on this much right here for now. Inverse cosine of minus 9.4 divided by 15.5. And that gives me this inverse cosine part. I'm going to multiply by 5 and divide by 768. Well, 851. So actually, if I round properly, this is beyond 5. There's more digits over here. So this would round to 9. Not that it matters, because the question said to round to the nearest hundredths, right? So I get 1.77 minutes. So that's my first way of solving this problem. Does that make sense?
Yeah, perfectly.
Okay, now let me show you another way of doing this. If you have the power of a graphing calculator, you can really get here quickly. What I'm going to do is this. I'm going to enter this function here. So 17.6 minus 15.5 times the cosine of 2 pi divide by 5. Well, I think it would be just fine, but I'd rather do it this way. I'm going to put my x there and then divide by 5. Okay, so there's my function. I could just graph this function on the standard trig window, except, it's not going to be nearly high enough. But let's start there, and then we'll change it. So I'm going to go to Z-trig, and probably, I do see a little bit. Then I'm going to modify this. I really don't care if it goes very negative. Yeah, I don't really need to worry about negative y values. So I'm going to make y min 0, and I'm going to bump this guy up to, actually, this gets kind of big. So let's say 35. Let's see what that does for us. Okay, that's helpful. So that's what my function looks like. And what I want to know is, at what value of t will this be equal to 27? Well, there's two ways of getting that from the calculator. And one way would be this. I'm gonna just graph y equals 27. That's a horizontal line. So there it is. And now what I would like to know is, what is the, as the calculator will call it, what's the x coordinate of that point of intersection? And I think my calculator will do that for me. Let me see here. Second calc. So I press the second key and then the calc, and I want intersect. And it wants the first curve. So just get any point on the first curve, and we've got it highlighted now. The curve. Second curve, well, you can see it's on the line already. Press enter again. And then it wants a guess. So in other words, click somewhere near the point of intersection. So I highlight it visually and press enter. And this is coming up with 1.7685. And that's consistent with what I had here. So if you know how to do it, the calculator will actually give you that as well. Now, really, the point of the course is to teach you how to do this. So in some way, that's maybe a better solution. But on the other hand, if your calculator skills are strong, this is a valid solution as well, and it gets us to the same number. Does that make sense?
Yeah, it does. Thank you.
What is the answer again?
Round it the way they want it. It's 1.77 minutes. And in terms of my calculator, if I pop this back up here, it's not the y coordinate, it is x. See, the y is 27. When is it equal to 27? Well, but on the calculator, you have no choice but to call it x. So the x coordinate is 1.77 if you round.
It also has a second answer. Would you just add pi to that?
It also has what?
A second answer. So it has.
Okay.
Yeah.
The second answer is this point here.
Okay.
So I have two ways of getting it. Since I have this thing on the screen already, there's no reason I can't just repeat what I just did. I press second, calc, intersect, and then I highlight the two curves. There's only two curves here, so if I just press enter twice, it'll work. But now it's asking me for a guess, and I'm going to start it close to this intersection. And here's another one, 3.23. Now I could also get that by starting from probably here. But it's not a matter of adding pi. It's unfortunately, it's more complicated. The period of this function is not 2 pi. It's 2 pi divided by 2 pi over 5. Maybe I should put it this way. Divided by 2 pi over 5. So in order to divide two fractions, I invert and multiply. Not equals, this is times. So those are going to cancel out. So the period of this function is 5. So what that means is I got this kind of a shape now, so I know my function does something like this. You know, and exactly getting a real good picture doesn't make any difference. But what I do know is this: it starts here and it ends at 5. Okay, so I've got a pair of intersection points here. So I know that if here to here is 5, then here to here should be 2.5. It'd be right in the middle. And we should be able to confirm this. Let's do a trace here. What I'm expecting is that minimum there should be at approximately x equals 5. So if I just trace down, find a minimum, I'm at really close to 5, right? A little bit less than 5, a little bit more than 5 there. So yep, it's at 5. So this x coordinate right in is 2.5. The one I computed is, let's use this number, 1.769. And then because the cosine curve is symmetric, in other words, this and the two halves here are mirror images of each other, this distance and this distance will be the same. So let's compute the distance from here to here. That's 2.5 minus 1.769. And oops, I forgot to leave that mode. So 2.5 minus 1.769. And I get 0.74. And from here to here will then also be 0.74. And in order to find that x coordinate, I would take 2.5 plus 0.74. And that gets me to 3.24. Now, I really hope that if I go back to my graph, and looks like I got to do this thing all over again. Second, calc, intersect, two curves, and initial guess. 3.231 is what I'm coming up with there. Well, I probably have some rounding issues in here, but you could do it by symmetry. or you could do it by finding the intersection points on the graph. Does that work?
Yeah, that makes a lot more sense. Thank you.
Yeah. Honestly, in my opinion, if you're on an exam and you're working against time, if I were doing it, I would probably do this. It's, you know, it's so fast. However, it does depend on every single keystroke being correct. So I would be careful. Okay. Any other questions? Okay. No? Okay. Let's then talk about which problems on this sheet we should solve. So I'm going to show you my copy of the exam review, and we're starting, 21 is the first candidate. So it asks us to solve this equation here. So right now I'm just looking for yes or no answers. Does anybody want to see number 21?
Yes.
Yeah,
Okay. 21 is in. Number 22 actually is over here. Graph this function, and I've written all over this, making it hard to see, but this is the function, y equals minus a half, tangent, etc. Anybody want to see number 22?
Yes.
Okay. Number 23, find the polar coordinates of the point that has rectangular coordinates 4 minus 4 root 3. Anybody like to see that one? Okay. Number 24, find the exact value of the tangent of the arc sine of minus 2/5. Would anybody like to see that one?
Yeah.
Okay. Number 25, find the rectangular coordinates of the point that has polar coordinates 2 comma minus 11 pi over 6. Anybody want to see 25? Okay, number 26, a pole is 3.2 meters tall. It casts a shadow 1.7 meters long. A tower casts a shadow 48.75 meters long. How tall is the tower? Would anyone like to see that one worked? Okay, number 27. Is this, well, we're given 2 points on level ground, distance from the a mountain, and let me see, we're given a couple of angles, and we're asked to compute the distance from A to B. Would anyone like to see that one worked out?
yes,
Okay. And number 28, use a half angle formula to find the exact value of sine pi over 8.
Yeah.
Yeah, okay. And 29, find the exact value of the cosine of 15 degrees by using a sum or difference formula. Would anyone like to see that one? Okay, and the last candidate for tonight then is the question number 30. It looks like that's on the next page. Yeah. We are given the fact that these two islands in the sea are 14 miles apart, and that the distance between these two islands is 9 miles, and we are asked to compute this angle here. But in principle, you could compute any angles. Would anyone like to see number 30? Okay, well, let's see how many we got here.
What was number 38? Or was it 28?
This one right here with the islands, this is number 30.
Okay, so 29 actually.
Okay, number 29 is the exact value of cosine 15 degrees by sum or difference formula. Is that one you wanted, Lucas?
Yeah.
Okay. Okay, did we get them all? All right, well, let's get at it then. As usual, these are, I've got a few to work and I'm not sure how long it will take me. So if this goes on longer than you want to be around, please feel free to log off after you've got what you need. I am, but in order to get hopefully to everybody's question, I'll just work these from the beginning to end. Okay, so number 21, we want to solve this equation, 1 minus cosine square x times cotangent x. Is equal to sine x times cosine of x. Oh, and I made a mistake. It is not solve the equation, it's prove the identity. So prove that this is true. And the way this usually goes on Alex, I think they want you not only to write out your steps, but give justification for each one. So what we would do to prove something like this is usually you start with a more complicated expression and simplify it. So right now I'm just copying that left-hand side, and then I'm going to take one step at a time and hopefully end up here. Now this is pretty simple. So my intuition is if I simply clean this thing up, simplify it, in other words, it will end up here. But if it doesn't, I'll probably be close enough. I'll see what to do. So first of all, sine square x plus cosine square x is equal to 1. So 1 minus cosine square x is sine square x. That's a sine square x times cotangent x. That uses usually what we call the Pythagorean identity for sine and cosine. Okay, now the next thing I would probably do is say, well, cotangent can be expressed in terms of sine and cosine. So first of all, actually, I think, well, let's just do it this way. Cotangent is cosine over sine. And I think that Alex likes to call those the ratio identities. I've seen them also called the quotients, but either way, it means divide. Now, this sine square x means sine of x times sine of x. That's the meaning of sine squared. So you don't really have to write out things in such detail as I am here, but whoops, I want you to see where it all comes from. Okay, so what I've done so far is nothing. I've just rewritten the meaning of this, but the idea is that this sign will cancel with one of those, and so I would call this algebra. Sine of x divided by sine of x is 1. Then what am I left with? Sine times cosine. So that's my proof, and that's probably what I would do. And let me see, is that what I wanted? Yep, it is. So we've proved that this thing is equal to that. All right, anybody have a question about that one? Okay, the next one on our list is number 22. Graph this function here, and oh my, that doesn't look nice. Let's get it copied out and see if we can make some sense of it. So y is equal to minus 1/2 tangent of x minus 3 pi over 4. All right, so let's see what we can say before we get into a bunch of detail here. If this were a sine or a cosine, you'd say that the amplitude is 1/2. But what I do know about this is the minus sign flips the graph top to bottom. So now it doesn't have, well, let's draw it as it does appear. The tangent curve looks sort of like this. That's the regular old tangent. And then if you take tangent and multiply it by a negative, anything, it's going to flip it over. So this is a minus tangent of x, has that kind of shape. So first of all, I know that the minus is going to flip this over. The 1/2 is going to shrink y coordinates by a factor of 2. So in other words, if some point without this would have given me a y coordinate of say 1, that would reduce it to 1/2. You divide it by 2, and then that would make it minus 1/2. Flip it around the to the mirror image on the other side of the x-axis. This part gives a phase shift of 3 pi over 4 to the right. Subtractions shift to the right, additions shift the graph to the left. All right, so let's, and I don't have a multiplier on x. And, you know, I could emphasize that by saying I have 1 times x. So the period is going to be just exactly what it was before. The period for the tangent function is not 2 pi, it's pi. Okay, so let's see what we could do to just to get our bearings here. The normal tangent curve, just y equals tan x, has a shape sort of like this. It goes through the origin. So let's ask ourselves, first of all, what happens to that point? Well, it gets shifted to the right by 3 pi over 4. So the new tangent,
Wait, I
new
thought it
version of the
was negative,
tangent, I didn't hear the question or comment.
I thought it was a negative though.
It is a negative, but that shifts it to the right. Let me show you something easy, and you'll see it. Let's suppose I took this curve, y equals x squared. Now that's just a parabola that opens upward, right? And now this one, I'm going to take x minus 2 and square it. Whoops, I got 22. I wanted to. And for zoom, I'll take the standard window. So there's y equals x squared, and there's y equals x minus 2 squared. That vertex has been shifted to the right. And that probably seems a little bit counterintuitive, because if I added outside of the parentheses, it has the opposite effect. That will shift it up rather than down. So adding inside the parentheses will shift the graph to the left. Subtracting inside the parentheses will shift the graph to the right. Adding outside of the parentheses will shift the graph up, and subtracting outside the parentheses will shift the graph down. Okay. Does that address your question, Lucas?
Oh yeah, it just when you rewrote the phase shift to the right, you show a positive 3/4 or 3 pi over 4.
Yep. Oh, okay. Well, let me finish. This is the y-axis here. This is the x-axis. I haven't drawn my graph yet. So now this point that was formerly at x equals 0 is now going to be at 3 pi over 4. So let's kind of get things started here. I need to draw in my asymptotes. This is the tangent is sine over cosine. So you're going to have a vertical asymptote whenever that denominator is 0. The denominator is 0 when the cosine is 0. Cosine is 0 at pi over 2. So that is pi over 2. And this is minus pi over 2. And that is 0 on the standard, the uncomplicated y equals tan x. So this point here now gets shifted to 3 pi over 4, which is, that's pi over 4 there. So it gets shifted over to the other side of the that vertical asymptote. So let's get this sketched in. Pi over 2, that's pi, that's 3 pi over 2. And that intercept went here. Now, if you think about it, the original tangent function has an intercept at 0, but then it has another one at pi. So right there. So that shift actually didn't do anything, because I had another copy here. So this got dragged over here, but this one followed into there. So that shift by itself seems not to be doing much to me. Okay, the next thing I'm going to do is flip it over and multiply it by 1/2. So now when I flip this over, I'm going to get this kind of a shape. And similarly, similarly here, I got to get my, oh, my camera quit. Ah, shoot. Let's try a restart. Okay. Okay, are you all seeing that again? Yeah, no?
Yeah, we see it.
All right. So this point moves by 3 pi over 4, which is just right directly in the middle of the next period. So so the problem is, I think I changed scale here. Oh, I see what happened. All right, that's wrong. Pi over 2, pi is here, and the next branch comes up here. Okay, so I changed scales, unfortunately, on these two drawings. 0, pi over 2, 3 pi over 2. So 3 pi over 4 is right there. It does make a difference. So I got to resketch. And it would be helpful if I kept the same scale. So I'm making each one of these pi over 4. That's pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 4. Okay, so originally from minus pi over 2 to pi over 2 gets this branch, and that shifts now by pi over shifts to 3 pi over 4, which is right here. All right. Then I want to find out what happens to my asymptotes. Pi over 2, I have to shift that right by 3 pi over 4 units. And so this is 2 pi over 4 plus 3 pi over 4 makes 5 pi over 4. Right here. And let's see, that was pi over 2. How about minus pi over 2? So minus 2 pi over 4 plus 3 pi over 4 makes minus pi over 4. And let's see. And the distance between these is pi. 1, 2, 3, 4. I think my scale went nuts here. What happened? That looks okay.
Wait, wouldn't that last number be 5 pi over 2, not 5 pi over 4?
This is minus 2
On the graph.
pi over 4, right? That's different number? Which one are you talking about?
On the graph. You go 2 pi or pi, half pi, pi, 3 pi over 2, 2 pi, 5 pi over 4.
Oh, yes,
Wouldn't that be 5 pi over 2?
yes, it is. But this is what's bothering me. Maybe I'm okay here. Oh, this is plus pi over 4. All right. I believe that. This is inaccurate. Okay, so now let me check. 1, 2, 1, 2, 3, 4. And these are in units of pi over 4. So that gives me a period of pi, which is correct. All right, now, so right here at 3 pi over 4 is my intercept. Then when you go halfway between here and the asymptote, you should get a height of 1. However, this graph, this function is being multiplied by minus 1/2. So the new height, instead of that being plus 1, is going to be minus 1/2. Pretty hard to see in there, but let's call that 0.1. That's 0.2. And then similarly, if I go 1 click to the left, it's going to go up by 1/2. And that's 0.3. So 0.2 is pi, comma, minus 1/2. And 0.3 that I made is that guy right there. That one is pi over 2 plus 1/2. Okay, and now I know in general that these curves have this kind of a shape. So I'm just going to try to sketch it in there. And it's hard to be exact, but that's more or less accurate. All right, confirmation. All right. Here's my function up here, minus 1/2 times the tangent of the quantity x minus 3 pi over 4. And let's take the standard trig window and see what that does for us. Well, in general, not too bad. It's got the right kind of pattern. We're seeing an intercept over here to the right and then another one to the left of the origin. And that would make sense if I made another copy of this over here. That intercept is going to be a little bit to the left of the origin. Let's look for this guy right here and see if we're at the predicted point. We're predicting 3 pi over 4. So 3 pi divided by 4, about 2.36. And go to our graph and try tracing. Pretty close, 2.356 here. So that's looking pretty good. So there is the hard way of sketching this function, and we do it by applying these transformations, a right shift by 3 pi over 4, flipping it over, and then shrinking along the y-axis by a factor of 2. Okay, any question about that? On tangent, cotangent, secant, and cosecant, what I have found in general to be the most helpful is to first sketch in the asymptotes. Then you get 1 or 2 points in the in between them. And at that point, you've pretty much got things narrowed down if you know the general shape of the curve. All right, I'm ready to move on unless somebody wants to follow up on that. Okay, that was 22. Next one up is number 24. Find the exact value of the tangent of the inverse sine of minus 2/5. Okay, now there are multiple ways we might approach this. But one way would be this. Remember, if you're working with sine, cosine, tangent, etc., you're starting with an angle and then you're producing a number, right? This one does the opposite. It starts with a number and it produces an angle. So you can sort of think of this, if it helps, think of that as some angle theta. And so what do we know about theta? Well, theta is the angle. Well, I could write it this way: inverse sine of minus 2/5, but you could also write it this way: the sine of theta is minus 2/5. Now that actually helps me a little bit. It tells me that the x, if I'm going to draw a terminal side for this angle, you could either make the x coordinate minus 2 and the y coordinate 5. We'd be way up here for a ways, right? Or you could flip the negative here and say you go over 2 to the right and then down 5. It would give you the same. It would give you the same line. And this is the one that the inverse sine will give you, because the inverse sine of x is always going to produce an angle that is at most pi over 2 and at least minus pi over 2. The reason is the inverse sine, inverse cosine, etc., always return the angle that is as close to the origin as possible. That gives the desired value. So I'm making this 1 here. So the sine has that kind of a shape. And it's, you say this height right here, is it going to be achieved again? Sure, it's going to be over there. Or this height here, it's going to be hit over here again. But you're always going to take the one that's the closest to the origin. So it's going to be this negative angle. So here's theta. And I have a triangle now. Whoops, drawn a little bit off, but that'll be all right. So that the sine is opposite over hypotenuse. The opposite is going to be -5. The adjacent is +2, and the hypotenuse we'll get from the Pythagorean theorem. So 2 squared plus 5 squared, take the square root, that's the hypotenuse, and that's 25 plus 4, 29, square root of 29 is this side of the triangle. And now we are ready. Can you compute the tangent of that angle? Yes, sure we can. It's opposite over adjacent. And as a matter of fact, once I have the triangle drawn, it really doesn't matter to me what this outer function is, because I can do all 6 trig functions once I have this much information, right? Okay, anybody have a follow-up to that?
What exactly was the question? I had to step out for a sec.
The question is find, trying to get my, find the tangent of the inverse sine of -2/5. And the strategy to solve it was draw a picture of this angle that has a sine of -2/5. Oh my goodness. Did I do that right? Oh, I'm so sorry, I made a mistake here. I did arc tangent rather than arc sine. Okay, well, scrap that mistake. It's a great solution, but to a different problem. I think I looked at this outer function here and turned things around. Okay, now most of the explanation is the same. You're just gonna watch a shorter version. Okay, the sine is -2/5. Sine theta is opposite over hypotenuse, or when I'm drawing on the x coordinate like this, it's going to be the distance. If I'm like so, right, it's going to be the y divided by the hypotenuse. Okay, so what we know is the sine is -2 divided by 5, and now we need to compute the x. So x squared plus y squared is equal to 25. So x squared equals 21, and x is root 21. Okay, now the question is, that's this part in here is the angle theta. So that's my angle there. What is the tangent of that angle? The tangent is the opposite divided by the adjacent. -2 over root 21. Or some people like to rationalize the denominator. You just multiply up and down by root 21. -2 root 21 over 21. So that is a new and improved solution to number 24. Okay. And this one that I wrote earlier, actually, it was all well and good if only I had a tangent in here, and I must put a sign out there. I think I reversed the things. Okay, that's 24. Next one is 27. So we have this picture of a mountain here. And let's read through this. And what I'm going to do as I read is I'm going to draw that picture in the abstract without the picture of the mountain. So I know ahead of time that I've got this kind of a triangle. This is A, this is B, this is C, and we're ready to fly. Okay, mountain officials want to build a new ski lift from B to C. Okay, so the cables for the lift run across here. The distance from A to C is 1,480 feet. So from A to C, this side is 1,480. They measure angle DAC to be 33. Well, there's a point D directly underneath. So DAC is 33. The angle DBC, so DBC, this guy here, is 23. What is the distance from A to B? That's what we're trying to compute. I'll call that X. And now we're going to try to solve this triangle. Okay, here's what we know. We've got a 33-degree angle here. From here to here is a straight line. That's 180. So, whoops. 180 minus 33 is 147. So this angle is 147 degrees. Now the sum of these three has to be 180. So we've got 180 has to be the total. Then subtract off what we've used up, 147 and 23. And we've got 10 left. So this one, 10. So I know all the angles and I know one side. And what we'd like to do is get this side here. Well, that is a classic setup for the law of sines. So we'll have X, or you could say AB, over the sine of 10 degrees is equal to, now just pick the other one we know, 1480. 1480 divided by 23, sine of 23 degrees. And so we just multiply through by the sine of 10 degrees. And we get an approximation on our calculator. I've got to switch over to degree mode. So I've got sine of 10 degrees divide by sine of 23 degrees times 1480. And that is 657.74 approximately. And this probably gave us inaccuracy to the nearest tenth of a foot. So 657.7 feet is the answer they're looking for. And fortunately, I got that last time I did it. Okay, any question about that one? Okay, is 28. Uh, 28 asks us to use a half angle formula, half angle formula to find the exact value of pi over 8. Okay, now there's two ways of approaching this. One would be just to quote the half angle formula. And let's see. And we have a list of identities. So we could look up our formula. Yeah, here we go. Sine of x over 2, or you could say theta over 2, is plus or minus square root 1 minus cosine x over 2. And that's probably the one to go with. So sine of theta over 2 equals plus or minus, you have to decide yourself. In other words, that it's not both. The formula doesn't tell you whether to use which one to use. All right, but we can figure that out. We know that the sine function, there's a couple of ways to thinking about it. Number one, the graph of the sine function looks like this. And on the interval from 0 to pi, the sine function is positive. So that tells me pi over 8, that's in here somewhere, definitely the positive option is the one we want. Option number 2, think about drawing the angle in standard position. This is pi over 2, pi over 4 is about here. So pi over 8 is an angle like this. And if I draw the triangle, opposite over hypotenuse is going to be positive. Once again, I come to the conclusion that I need a positive number here. So what good does this do us? Well, this angle is just half of that one. So, or in other words, start with this and double it to get that one. So the sine of pi over 8 is plus the square root of 1 minus cosine of twice that angle. Twice pi over 8 is pi over 4, all over 2. And the cosine of pi over 4 and the sine of pi over 4, for that matter, are the same. They're 1 over root 2. So we just got some algebra to do here. Okay, let's get a single fraction in the numerator. 1 is the same as root 2 over root 2. So I have root 2 minus 1 over root 2. That's all I've done so far is just the top. And now I want to take that result and divide it by 2. Well, I just put a 2 down here. That does it. And I suspect we can make this look a lot better. Let's multiply top and bottom by root 2. Okay, root 2 minus 1. Now, 2 times root 2 times root 2, oh, that's 4. And then there's not much you can do for the numerator. But the square root of 4 is 2. And that, after all, this is the sine of pi over 8. So sine of pi over 8 should be that number. By the way, when you do a long calculation like this, it's usually a good idea to double check. And sometimes you really have no choice but to, go back through and check each step and make sure it worked. But since we do have a calculator here, there's no reason that we couldn't verify that way. Let's take the square root of 2. Now I got to escape that first square root, subtract 1, and now that gets me out of the second square root. And then I want to divide the whole thing. Whoops. Whoops, I did not want that. Can I delete? Yes, I can. Okay, divide by 2, I think should do it. And then I could also try this. First of all, let's get into radian mode. And then take the sine of pi divided by 8. And they don't quite agree. Uh-oh. All right, let's try again. Oh, I see it. See this root 2 times that root 2 turned this whole product into a 4. You see that root 2? It disappeared. Needs a root 2 in there. And while that is numerically correct, it's more simple to distribute. This times this is 2. This times this is root 2. Take the square root, and the whole mess is divided by 2. All right, try again. Square root of 2 minus square root of 2. Divide the whole thing by 2. And that's the 3/8 we were expecting. All right. So I did not intend it, but I ended up giving you an excellent illustration of why it makes sense to check your work. All right, anybody have a follow-up on that one? Okay, the next one on our list for tonight is question number 29. Find the exact value of the cosine of 15 degrees by using a sum or difference formula. Well, before we can work this problem, of course, we have to know what the sum and difference formulas are for the cosine. The cosine of x plus y is equal to the cosine of x times the cosine of y minus the sine of x times the sine of y. Now that's for the sum. Actually, if you know this one and you know that the cosine is even and the sine is odd, then you can get the difference formula automatically. The cosine of x minus y, you go from here to here right by replacing y by minus y. Now, since the cosine function is even, cosine of minus y and cosine of y are the same thing, so you can drop the negative there. Here, however, the sine of minus y is minus 1 times the sine of y. So that, replacing this by a minus y, that minus essentially pulls through and cancels this one out here. So we get plus sine of x times sine of y. And this is the difference formula that the problem is referring to. Use the sum or the difference formula. Okay, so let's solve that problem. Here's our difference formula copied out, and what we want to do in order to get a 15 degrees in here is pick two angles that are different by 15 degrees. Well, 45 degrees, that's a special angle. 30 degrees, that's a special angle, and 45 degrees minus 30 degrees is 15 degrees. So it works just fine to compute cosine of 15 degrees as cosine 45 degrees minus 30 degrees, and then we use our formula up here. So it's the cosine of 45 times the cosine of 30 degrees plus the sine of 45 degrees plus the sine of 30 degrees. And now we convert these to the corresponding exact values. Well, the cosine of 45 degrees is 1 over root 2. The cosine of 30 degrees is root 3 over 2. The sine of 45 degrees is 1 over root 2, and the sine of 30 degrees is 1/2. And you can see we actually already have a common denominator here of 2 root 2. So that gives us this times this, root 3 plus 1 times 1 is 1. Root 3 plus 1 over 2 root 2. Now, that is numerically the correct answer, but ordinarily we would rationalize the denominator here. So you multiply the bottom, the denominator of the fraction, by root 2. So 2 times root 2 times root 2 would be 2 times 2 or 4. And then this whole thing also gets multiplied by root 2. And then distribute. Root 2 times root 3 is root 6. Root 2 times 1 is root 2. And there is our exact value for the cosine of 15 degrees. Okay, last problem for this part 3 of the final exam review is problem number 30. David is on vacation at a tropical bay that has 3 islands. He rents a boat on island A and plans to navigate to island C, which is 14 miles away. So we know that distance there. Based on the figure below, at what angle theta should he navigate to go to island C? So we're looking for this angle right here. So presumably he can take a sighting from here to here, and then if he can compute that angle, he knows the heading to proceed directly to island C. Now, given this triangle, the thing that you want to notice is that, first of all, we know all 3 sides. So this is the case of side, side, side. And we don't have any of the angles whatever. Now, at first glance, that might kind of look like it's a right angle, but we're not given that information, so we can't assume it. And in fact, I'm not. I think that it probably is not. We could check that, by the way, very easily. If this squared plus this squared is equal to that squared, we'd be all set. But if you check, you find out that that's not the case. So since we don't have any angles, we cannot use the law of sines. And here's why. If we wanted to know this angle, then the law of sines would allow us to say something like this. The sine of theta divided by 12 is equal to, well, either the sine of B over 14 or the sine of C over 9. But we don't know the measure of angle B or of angle C. So law of sines is out, and therefore that is why we must use the law of cosines. When you have side, 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 and you don't have a right triangle, then you have to use the law of cosines in order to find one of the angles. Okay, the law of cosines can be stated this way. A squared is b squared plus c squared minus 2bc to cosine of a. The key here is this, that this side, little a, you must have the opposite angle here in the cosine. And then whatever side is here, you leave you have 2 other signs, b and c in this case. So b and c have to occur here and here. So that's how the pattern is written. And what we can do, of course, is subtract b squared and c squared from both sides, and then divide through by 2bc, but that would leave minus cosine of a. So we multiply everything through by negative, and that makes, when we push these to the other side, they became minus b squared and minus c squared. Well, that flips them back to positive, and what started as a positive a squared turns into a minus a squared. So we get this fraction right here. Now at this point, all you have to do is plug in the numbers. 14 is the value of length of side B, 14 squared. The length of side C is this one right here, 9. So 9 squared, and then of the remaining side is 12 squared, and then 2 and BC appear here again. So all you do is plug this into your calculator and then take the inverse cosine in order to compute that value. So let's let's do that calculation. First of all, we're trying to get an angle in degrees, so make sure that we're in the right mode. Then we'll take this numerator is 14 squared plus 9 squared minus 12 squared. And we want to divide that by 2 times 14 times 9. And what that gives us, of course, this value here is not the angle A, it's the cosine of the angle A. So we simply take the inverse cosine of that previous result, and we get 58.14, etc., for angle A. Now, this says to carry computations to multiple places and then round it off to a tenth. So if we round off to a tenth of a degree, 58.1 is this angle right here. So that takes care of problem number 30, and that is the end of part 3 of the final exam review.